Hello everybody. In today's lecture we will be solving 1987 IMO problem number 1. It's a combo problem and here's a view of this problem. Let this notation, P sub n of k, represent the number of permutations of the set 1, 2 all the way to n which have exactly k fixed points. Here inside the parentheses we added a remark which explains what's a fixed point. Prove that this expression holds. This is what we need to show. And to begin with, what I will do is I will express, let's first denote the left-hand side of this expression as f of n. Let's call this f of n. So therefore, the question is asking to show f of n is equal to n factorial. So I will provide two different proofs. One is both combinatorial proofs. One is a very simple one, almost immediate. The second one using recursion. But before we begin, I want to make sense of this because this doesn't even look reasonable, right? So what does that mean? So consider the case, let's use this space here. So consider the case n is equal to 4, and the 4 elements are 1, 2, 3, and 4. This is our set, and the permutations I will just represent. For instance, this permutation 2, 3, 1, 4, I will simply write it for simplicity as 2, 3, 1, 4. I hope it's clear for everybody. Okay, so let's create the list of all the permutations that are available. Obviously, we can start with the identity permutation. Actually, let me just open some space here. Okay, so let's start with the identity permutation. E is equal to 1, 2, 3, 4, and then we have all the other permutations which will follow up. 1, 3, 2, 4, 1, 3, 4, 2, 1, 4, 2, 3, and 1, 4, 3, 2, and then we have those which begin with a 2, 2, 1. Okay, so let's identify the fixed points in this picture. So we can, obviously, this is a fixed point, that's a fixed point, it is fixed, it is fixed. This is fixed, this is fixed, those two are interchanged, they are not fixed. This one is fixed. Actually, let's first focus on the ones which will fix the 1. That's easy. And the other digits, all the other permutations start with 2, 3, and 4, so there's only those. How about the 2 being on the second place? So those 2 and those 2 as well. How about 3 being in the third place? Here, here, none here, and then 3 is here. And finally the 4 in the last location. 1, 2, 1, 2. Okay, so let's just clarify this. Okay, so now let's make the count based on our definition, I guess, right? So let's start with p sub 4 of 0 and so on. So p sub 4 of 1, p sub 4 of 2, p sub 4 of 3, and finally p sub 4 of 4. So we can first do the simple ones if you would like to. So for instance, how many permutations will fix everybody? Well, obviously this one. This permutation here fixes everybody, so we can get rid of it. So there's only one which will fix everybody. And how many permutations will fix 3 of them? That won't be possible, because if 3 of them are fixed, then the last one, the remaining one, has to be fixed as well. So there won't be any permutation qualifying for that. The rest is counting carefully. So let's count those permutations which have no fixed point in it. All of these have fixed points. This one doesn't have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 in here. And how many with one fixed point? 1, 2, 3, 4, 5, 6, 7, 8. 8 in here. And finally, how many with 2 fixed points? The remaining ones, I guess. 1, 2, 3, 4, 5, 6. 6 of these. Well, it is not surprising that the total number of permutations here is equal to 24. We have 24 sequences of 4 numbers here. And obviously, if I add all these numbers that I got, so the sum k equals from 0 to 4, p sub 4 of k is equal to 9 plus 8 plus 6 plus 0 plus 1, and that's 24 as well. So this is no surprise because these two numbers has to match up, right? This is the total number of permutations, and the total number of permutations can be written in this fashion. But what's so strange is that the total number of fixed points in all the permutations, right? So when you look at this expression here, really the interpretation for f of n is that so f of n, let's write that down. So f of n is equal to, using this summation, so expanding this summation sum formula, p sub n of 0 plus 1 times p sub n of 1, and so on. 2 times p sub n of 2, and then n times p sub n of n. So what's so strange is that the sum of all the fixed points in all the permutations, so this is the number of permutations with 0 fixed points, and okay, so well, that one is redundant. How about here, the number of permutations with 1 fixed point, and this is 1, so you multiply it by 1. The number of permutations with 2 fixed points, and then you multiply it by 2. So therefore f of n represents the number of all fixed points in all the permutations. So going back, for instance, to the case n is equal to 4, the number of all the fixed points, so all we do is we count the highlighted ones, obviously. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. An alternative way to well, instead of counting this one by one, all these highlighted numbers, what you can do is you can directly use the definition. F of 4 is just 0 times p sub 4 of 0 plus 1 times p sub 4 of 1 plus 2 times, so which will give you basically the same number as we did, p sub 3 plus 4 times p sub 4 of 4. That one vanishes, so 1 times p sub 4 of 1, we just got it as 8. Or actually, even if it vanishes, let me just write it regardless. So it's just 0 times p sub 4 of 0 is 9 plus 1 times p sub 4 of 1 is 8 plus 2 times p sub 4 of 2 is 6 plus 3 times p sub 4 of 3 is 0 plus 4 times p sub 4 of 4 is just 1. And not surprisingly, so these two vanishes. We have 8 plus 12, which is 20, plus 4 is 24. So we need to give a reasonable answer why this number comes out as 24. This is obvious, right? So this number coming out as 24 is obvious because we have 24 permutations, and this is a count of all the permutations with k fixed points for k equals from 0 to 4. But this one is quite surprising to get 24 here as well. So that warrants an explanation, and the explanation is not too difficult. Let's focus on the case n is equal to 4. Let's focus on all these permutations. So here we just realize that each of the numbers 1, 2, 3, and 4 is a fixed point of n minus 1, 4 minus 1 factor, or 3 factorial permutations, right? So for instance, consider the permutations, so where I is equal to 1 is a fixed point. So if the permutations where I equals 1 is a fixed point are these permutations, right? In all these permutations, 1 is a fixed point, and there is no other permutations where 1 appears in the first position. But then you can just realize that the number of these permutations, the number is simply equal to all the remaining 3 terms, their permutations, right? So it's just 4 minus 1 factorial. But then we can pick any one of these numbers. So this is the position. These are permutations where 1 was fixed, and we can also find the permutations where 2 is fixed, right? And so on. 3 is fixed and 4. So there's 4 different ways we can choose the fixed permutation, and then the remaining elements, n minus 1 elements, or in this case 4 minus 1 elements, we just look at the permutations, which is just 4 minus 1 factorial, and we come up with the 24, and that makes sense. Now, to generalize this proof, so let's just now write a little bit more of a rigorous proof. So each j in S is a fixed point of n minus 1 factorial permutations, which is pretty clear, right? All the remaining elements, they can be permuted in n minus 1 factorial ways. And what are those permutations? If you would like to rigorously write it in terms of this notation, F notation here, the permutation is the F permutation. So the permutations, basically all these n minus 1 factorial permutations are those of the following form. F of I is mapped to J for whenever I is equal to J. Otherwise, it's mapped to another function, G of I, for which is a restriction of the function f onto all the elements not equal to J. And that's it. So where G is a permutation of the remaining n minus 1 elements of the remaining n minus 1 elements of S, like that. N minus 1 elements of S, namely S minus J, right? So you just simply remove the element J from the set. But then, okay, so once we say that, because each J satisfies this property, so there are n different ways we can select. So select J in n ways, and once you selected the J, there are n minus 1 elements remaining, n minus 1 factorial permutations. So therefore, and n minus 1 factorial ways to choose, to select, let's use the same word. So select J, and then there are in n different ways, and then n minus 1 factorial ways to select the permutation G, right, of the set S minus that. And as a result, f of n therefore is simply equal to the number of all the fixed points in all the permutations is therefore equal to n times times, and because it's an AND condition, times n minus 1 factorial, which is equal to n factorial. And it is quite straightforward, no tricks, and that's it. However, the downside of this solution is that it doesn't explain to us where these numbers come from, basically, right? So we have no clue about how these numbers 9, 8, 6, 0, and 1 comes from, or the nature of the. So let's say this solution is great. However, a remark: no clue on the behavior of p sub n of k. But then here's an alternative proof, or well, yeah, let's give a second proof to this problem. I will go ahead and recursively define p sub n of k, but before I do that, let me remind you of the definitions we have so far. So f of n, we decided to call this sum, the number of all fixed points in all the permutations, k equals from 0 to n, as f of n. And also we established earlier that it is quite easy to establish that the number of all the permutations with k fixed points, where k ranges from 0 to n, is obviously equal to the number of all the permutations, which is simply equal to n factorial. So let's call actually this equation as number 1, and this one will be useful again. That's number 2. Now the third one, and this is my claim, I will recursively define p sub n of k. Okay, so let's do it together. I guess before I give the claim, sorry for that. Okay, so because we will use recursion, so let's focus on the set S, which had the elements here, and I'm just going to consider the situation for the last element. Okay, so n, the nth element. So depending on whether n is a fixed point or not, we can count this function here. So we have, I claim, 3 cases, actual 2 cases, but for now let's just focus on 3 cases. So n is a fixed point. So the first case is n is a fixed point, not a case, sorry, three possibilities. Either n is a fixed point. So if n is a fixed point, and because we want to have k fixed points, so one of them is already known, we have n minus 1 remaining terms. Among all the n minus 1 remaining terms, there has to be k minus 1 fixed point. So that number is equal to, so the first situation will count this many of them. Plus, well, in the second situation, n is not a fixed point. However, it's part, and it belongs, or n belongs to n, belongs to a cycle of length 2. So if n belongs to a cycle of length 2, what we mean by that is that consider the permutation that takes the element, let's say m in s minus n. Okay, there we go. So let m be any number in the set s not equal to n. Then the permutation which takes m to n, and then it takes n to m. So that's what I mean by a cycle of length 2, right? So in this permutation, it's good. So just to give you an example from what we did early on. Okay, an example would be, so 4 would be cycling with another number. So let's say 4 and I don't know. So let's say 4 is cycling with 3 here, right? So 4 is cycling with 3 here. Do you see that? Yeah, something like that. Okay, so going back to our thing, so we have, okay, so let's just leave it like this. So you have, so n is not a fixed point, and it belongs to a cycle of length 2. So how many? So therefore, the remaining, we have n minus 2 elements remaining, and we need to have among these n minus 2 elements k of them as fixed points, because so far neither m nor n are fixed points, right? So we have p of n minus 2 elements remaining, and we need k permutations for these. But then there is n minus 1 ways of choosing this m randomly from the set s minus n. So n minus 1 times p sub n minus 2 of k. and finally plus, okay, so finally the last situation is that n is again not a fixed point, and n belongs to a cycle of length greater than 2, greater than 2. So a cycle of length, say 3. So what we mean by that is, using the same probably notation, let me just open some space here. So what I mean by that is, consider, so let m be in S minus n again. So we pick an element m such that f takes m to n, and then it takes, sorry, let's keep using the other notation. It takes n to say r, and r will be mapped to whatever. But do you see that n is part of a cycle which has size at least 3 here, as you can see. Now, so to count the number of permutations which satisfy this situation, so to count the number of permutations with this feature, so what we can do is, again, there is n minus 1 ways to pick m, so no wonder we will still have an n minus 1 here. And then we will open a bracket here. This one will be slightly messier, as you can imagine. And all I need is, I will find a one-on-one bijection between this count, and instead consider this permutation, which is defined on, instead of on the set S, this permutation G is defined on S minus N, and it simply sends M directly to R by skipping n. So what it means, basically, what I'm saying is that G coincides with F for all the other. So it sends M to R. So that's the only distinction, right? But everywhere else it coincides. These two permutations would otherwise coincide. They send the same elements to the same elements, basically. So here G would have to have k fixed points, right? But obviously M is not such a fixed point, right? So therefore, for a given M, and there is m minus 1 ways of choosing that. So given M, I claim there are this many permutations: n minus 1 of k minus p of n minus 2 of k minus 1 permutations which satisfy permutations G which satisfy this thing. And the reason is that, so from all the permutations with n minus 1 elements in them having k fixed points, we don't want m to be a fixed point. So as a result, I need to subtract those where m is considered a fixed point, because once m is a fixed point, there's n minus 2 elements remaining, and you need only k minus 1 fixed points, right? So that's the remaining part. So therefore, that would be simply Pn minus 1 of k minus Pn minus 2 of k minus 1. And you don't have to worry about the situation of R because of the symmetry again, right? So that's, but try to convince yourself that this is in fact a valid recursion. I will not go into confirming it. So for instance, you can easily check if this holds for the case n is equal to 4. So I will just leave it to you as an exercise to confirm that the recursion definitely holds in this case. But then going back to our result, to conclude the proof, all we needed, so remember, so we were given these equation 1 and 2, and now we also know this recursion, which we can call it as number 3. So now to conclude the proof, remember our goal was to show that f of n is equal to n factorial, right? The number of permutations in the number of fixed points in all permutations is equal to n factorial. That was the goal. So the way to do it then is, yeah, we can just simply substitute things inside. So what I will do is, what you can do is, let's do it that way. So all you do is you substitute this expression here into the definition of f of n. Similarly, you will make use of this as well. So you basically plug in 2 and 3 into 1, and from there you will get this very nice closed form, recursive expression, n times f of n minus 1. And once you get that, also making use of the initial conditions, by induction you can generalize and you can find that f of n is simply equal to n factorial. So make sure you use induction here, and you use the induction step to show this result, which is really nice. Okay, finally, before I conclude this, I know it's been a long video here. Final step is, what are some interpretations? I would like to make at least 3 remarks. For instance, if you go back to the original problem, well, the case n is equal to 4, what it means here that there is no fixed point is basically counting the number of derangements, right? P sub 4 of 0 would simply be the number of derangements, and what you can do is, using the recursion that we got now, for instance here, you can easily calculate the number of derangements. So let me so just use this expression. So substitute k equals 0 here. Obviously minus 1, so p of anything minus would be simply by default, by convention, equal to 0, and p sub if the index of our p function is less than the number of fixed points, again that should be by convention equal to 0. But once you do that, you consider those, then the first remark would be the number of derangements. Meaning the number of permutations with no fixed point is given by this, so p sub n of 0, and using the recursion that we just produced, you can easily see that this is simply equal to, so when you look at it, if you want this to be 0, right? So k will be, sorry for that. So you want this guy to be 0, so 0 minus 1 is negative, so this term will simply vanish, and so this term here will be, this one will remain, I guess, n minus 1, so let's write those terms. So what you should be able to get is the following: p sub n minus 2 of 0 plus n minus 1 p. Make sure you confirm you get that result. But this is a beautiful recursion to obtain the number of derangements. Obviously, everybody knows that there is a closed form formula for number of derangements. I won't go into that topic today. But secondly, there are 2 very nice interpretations of the results that we found today, namely that the number of all the permutations, the number of all the fixed points in all the permutations, 0 to n, being equal to n factorial. Basically, if someone has n letters and n envelopes, and you just randomly put the letters inside the envelopes in a random way, the probability that the probability of exactly k letters being put into the correct envelope would simply be equal to, because and that we have n factorial different ways of putting the letters into the envelopes. So this is just p sub n of k, right? So those that have the correct letters into the correct envelopes, right? The fixed points basically, and that's pretty beautiful, right? So secondly, if you further focus on the following, you would also recall that so this is thirdly a second interpretation actually. The expected, how about this? The expected number of letters that are placed correctly. So those one would be this. So given this probability, all we need is the following sum of you can say from k equals from 0 to n k times, so k letters are placed correctly with this probability, right? But then the numerator here is simply the definition for f of n that we established early on, right? So f oh, sorry for that. Yeah, so we no longer need the whole thing is f of n, my bad. So this whole thing is f of n. So f of n over n factorial would be as I said, the expected number of letters that are placed correctly. But f of n we just established is equal to n factorial, so that thing is equal to 1. So if you have, let's say, 10 letters in front of you and 10 envelopes, and you randomly put the letters into the envelopes, the chances that the envelope will be placed in the inside the correct the letter will be placed inside the correct envelope will be just one out of these 10 envelopes. So it's a striking result as well, a beautiful interpretation as well. So let's stop here and hope to see you guys in our next video.